Okay. Okay, so we are live on YouTube. Okay, so we are live on YouTube. Okay, so we are live on YouTube. So I welcome everyone, one and all, for this edition of the NSF Wednesday Colloquium. For this edition, we have Professor Mohit Randeria from the Ohio State University, who is going to talk about superconducting transitions in materials. But before Professor Randeria comes and gives his colloquium, I just wanted to tell to one and all who have joined us in YouTube channel, the TIFR Platinum Jubilees YouTube channel, as well as those who are in the Zoom, that the NSF Wednesday Colloquium is a weekly series, and we sort of host the world's most foremost experts in the hope that all of us within TIFR, especially within the natural sciences faculty, get a chance to listen to sort of the contemporary frontline research in one specific area of natural sciences and discuss amongst ourselves the implications of it so that the broader perspective emerges. And this idea was put in for the first time by our own founding director, Professor Homi Bhabha. And we have been very fortunate that because of hard work of many of the colloquium coordinators and the academics here, we have continued this series from very inception of TIFR. So welcome again. And I have my colleague, Professor Rajdeep Sen Sharma, who is going to formally introduce Professor Mohit Randeria. Rajdeep actually did his PhD with Professor Randeria. So, Rajdeep.
Hi, thanks, Jyotishman. I hope you can all hear me. So it's a pleasure to introduce Professor Mohit Randeria. Actually, Mohit probably does not require an introduction to many people here, but there are a lot of new people, students, postdocs, new faculty. So let me give a formal introduction. Mohit Randeria did his PhD from Cornell University, and then after various stints, he had actually been an assistant professor at Stony Brook. Then he moved to Argonne National Lab for a while. And then for a period of about 10 years, Mohit was a professor here at Tata Institute of Fundamental Research in this very department. And also that's where my association as a student with him started. In 2004, he moved to the Ohio State University, and he has been there since that time in Ohio State. Mohit, of course, is very well known for his work on strongly correlated systems in general and on superconductivity in particular. His work on both what is called BCS-BEC crossover, which is a theory of strongly interacting superfluids, and then his contributions to the field of high temperature superconductors, which again he led for quite a long time, has been legendary. Mohit has been awarded various prizes, the ICTP Prize, the Santi Swarup Bhatnagar Prize. He has been elected a fellow of the American Physical Society, and most recently in 2022, he has been awarded the very prestigious John Bardeen Prize, which actually talks about his contributions to, the citation talks about his contributions to BCS-BEC crossover, to high TC superconductivity, and the third thing which he is going to talk to us about, he has recently been involved in deriving very universal bounds on what is the largest possible transition temperature of a superconductor, and this work has also been awarded with the Parabolic Prize. So, without any other delay, let me hand you over to one of the foremost experts in superconductivity, Professor Mohit.
Okay, thank you so much, Radhi, for that kind introduction. So everyone can hear me and see my mouse?
Yes. Perfect.
Okay, should I change it to a laser pointer? Is that better for people?
That is better. That is better. Yeah.
Okay,
Jyoti,
fantastic.
you should stop pinning me probably.
Okay, the next question is, I will not be able to see chat. So if there are some very urgent questions, either Radhi or Jyotishman, will you be able to
absolutely will point
that and stop me? What I could do is stop at some points and ask if there are questions. Okay? Okay, thank you very much. So actually, I am having some trouble navigating with this pointer. So, okay, good. So good afternoon, and it's very early morning for me. But I'm really grateful for this opportunity to present some recent work that we have done on upper bounds on the superconducting transition temperature. So here is a outline of the things I want to talk about. I will have a very long introduction so that people who are outside the field hopefully can follow what's going on. This is work done with two graduate students, Nish Varma, who is going to move to Columbia starting this fall, and Tamagna Hazra, who was my graduate student and is now working at Rutgers. And our work, or at least part of it, has appeared in the papers that are indicated here. Let's start with the basics. So what is superconductivity? The name derives from the fact that many materials, when cooled below a certain temperature, go into a state with zero resistance. This was discovered more than 110 years ago in the lab of Kamal and Owens in Leiden. And in fact, this is his original data on mercury, which shows that the resistance goes to zero below 4.2 Kelvin. And this temperature at which this happens is called the transition temperature, Tc. The second major fact that you need to know about superconductors is that if you put a superconductor in an external magnetic field, at least for sufficiently low fields, once the system goes superconducting, then the lines of magnetic flux are totally expelled from the system. So not only is R equal to zero, the magnetic field B also is equal to zero inside superconductor. Now, all of this was known so many years ago, but the theoretical understanding of superconductivity remained elusive for a very long time. Of course, this being a quantum effect, perhaps it's not surprising that it took, 1911 was too early to even understand conduction, let alone superconduction. But nevertheless, metals are understood within a few years of 1926, which is when quantum mechanics was developed. But superconductivity was first understood only in the late 1950s in this monumental work, which is now universally called the BCS theory of superconductivity after the originators Bardeen, Cooper, and Schrieffer. And they were able to show how there was a macroscopic manifestation of quantum mechanics that led to the absence of resistance and indeed also the expulsion of flux. I just want to point out that John Bardeen was the only winner of 2 Nobel Prizes in physics, in 1956 for the development of the transistor, and in 1972 for their work on BCS theory.
Mohit,
so this theory, yes.
Mohit, could I just ask a quick question before you proceed? The idea that you have a zero resistance that came from this fund. I've always wondered about the detection limits, or looking at what could be measured as zero.
Right. So that's a very good point. So the thing is, zero resistance means the following: that resistance is voltage divided by current. So you have a finite current passing through the system, but there is a zero voltage drop across your sample. Now, of course, if you have any voltmeter, you can never be sure that you're measuring zero. You can only say that your voltage is below your noise limit.
Right.
So I think the answer is that it is below any noise limit that anybody has ever been able to detect in the lab. And theoretically, we know that it should be strictly zero. And there are other consequences of it, such as the persistence of permanent currents, superconducting currents, and their lifetimes, and so on, or the existence of the Meissner effect. And all of those are seen in the lab. So therefore, we really do believe that it's zero.
No, yes, absolutely. I agree with that. What
Okay.
I'm saying is the fluctuations around zero is something that is not detectable. That's what, at least.
That is correct. At
right.
sufficiently low temperatures, there are absolutely no fluctuations.
Okay. Great. Thank
or
you.
the lifetime of a persistent current is larger than the lifetime of the universe.
Sure.
Certainly larger than the lifetime of any graduate student who would be willing to measure, but lifetime of the universe.
Great. Thank you.
Okay, so this theory was so successful that not only did it really explain everything that was known at the time about superconductivity, but it had implications and an impact on things very far from superconductivity. So very soon after that, here are the two papers which were cited in Nambu's Nobel Prize, where he takes the idea from superconductivity into particle physics. And here is Higgs's original paper, where he says that what he's going to derive in 1964 is really just the is the relativistic analog of what was done for non-relativistic superconductors by Anderson. So these are not things that BCS were setting out to solve, but they're the concepts that they introduced and the ideas that came out from that theory were extremely important in disparate areas of physics. So these are examples that I've already given, but the Ginzburg-Landau theory of superconductivity had a huge impact on critical phenomena and the development of effective field theory by Wilson. It had a huge impact on liquid crystals and soft matter physics as developed by Dejean and others. Okay, this was where people saw topological excitations in ordered media, like Abrikosov's work and Koslitz-Thouless's work. Tunneling spectroscopy was developed to measure the superconducting gap. The Josephson effects, which underlie present-day applications of superconductivity, were presented for the first time by Josephson. So all the names that I have here in blue are people who won Nobel Prizes for the contributions that they made to science. The superfluidity of helium-3, pairing in nuclei, superfluidity in neutron stars, color superconductivity, ultra-cold atomic gases. So the work of BCS and superconductivity in general had an enormous impact all across physics. But it also had a rather important practical impact. So interestingly, not only did the idea of the Higgs phenomena and the Higgs boson come from superconductivity, but in fact, the discovery of the Higgs boson was also helped by the existence of superconducting magnets, which are used at CERN. And even if you don't really want to worry about its implications for physics, superconducting magnets are very important in real life, so that at this point, almost all magnets in MRI machines in every hospital across the world are in fact superconducting magnets, because these are electromagnets, but once you have superconducting wires which have been cooled down below their transition temperature, then there are literally zero ohmic losses, because I squared R is equal to 0. And the cost of cryogenics and the cost of making these wires is more than offset by the saving on electricity. Thinking about the 21st century, it's also very important to note that superconducting qubits are amongst the most promising platforms for doing quantum computation. So everything that you read in the popular media about quantum computing is largely based on what experiments are being done at Google and IBM and other companies using superconducting qubits. The only other technology which is sort of competitive with superconductivity is that of trapped ions. But this takes me very far from the topic of my colloquium, so let's leave it at that. So now, superconductivity is obviously fascinating, but you might ask, how ubiquitous is it in nature? So if you look at the periodic table, then everything which has been colored either in blue or green, in fact, goes superconducting at some temperature or the other. But superconductivity comes in many shapes and sizes. You don't have to stick to elements. Here are the crystal structures of a large number of elements. The borocarbides were discovered by Professor Nagarajan and collaborators at TIFR, actually. But the magnesium diboride, the high TC cuprates, the fullerides, the iron pnictides. And amongst the most interesting superconductors were discovered some 2.5 years ago at MIT, where carbon, which was not marked as superconducting here in the periodic table, actually does go superconducting. So graphene is a well-known form of carbon, just two-dimensional sheets, a honeycomb lattice. And if you take two layers of graphene and twist them relative to each other, you get twisted bilayer graphene. And if you choose the angle just right, then it's called magic angle twisted bilayer graphene. And now there are some tri-layer cousins of that also. And these systems go superconducting. Okay? So then one might ask, if it's so ubiquitous, why aren't its applications so ubiquitous? And the answer is that the transition temperature for superconductivity happens to be quite low. So if you look at the plot of the transition temperature on the vertical axis versus time on the horizontal axis, and starting with Camelin zones, you can see that in the mid-1980s, this graph had plateaued. You wouldn't have drawn this line which was rising. And in fact, that's the time I was in graduate school when people told me that everything that should be known about superconductivity is already known, and we aren't going to teach you much of that in college or in university. Well, the year I graduated with my PhD was the copper age of superconductivity, when suddenly the transition temperature jumped from the 30 kelvins to the 100 kelvins to the discovery of the cuprate superconductors, copper oxide-based superconductors. More recently, we entered the iron age in this century, when superconductivity in the iron-based superconductors jumped all the way up to 55 Kelvin, or possibly even in some cases up to 100 Kelvin. And even more recently, we might have entered the hydrogen age of superconductivity, where the transition temperatures in the 200 to 250 Kelvin range are very well known. There are even some unconfirmed and controversial reports of superconductivity at room temperature. One of the downsides of these hydrogen-based materials is that you have to make them and keep them at ultra-high pressures. Okay, so these are at 100 GPa pressure levels. So 1 gigapascal is 10 to the 4 atmospheres, and pressure at the inner core of the Earth is 330 gigapascal, so 1/3 of that. So in that sense, they may not have very immediate applications. So if one looks at this graph, it seems like TC keeps on rising. And in fact, there is no limit to TC if you express it just in Kelvin, because an extreme example is that people estimate that the TC of the analog of superconductivity in neutron stars is possibly some number like 10 to the power 9 Kelvin. And the reason there is that the density of matter in a neutron star is extraordinarily high. So all the energy scales there are huge compared to metals or other systems that people study on Earth. Excuse me. So a different way of looking at TC is to make this so-called Mura plot, where the vertical axis is the log of the critical temperature TC, and the horizontal axis is the log of a Fermi temperature, which I can tell you more about soon. But right now, let's just say that it's a characteristic temperature or energy scale in a metal. In fact, this plot I'm using mostly for motivation, because first, you can hide a lot of sins in a log-log plot. Secondly, there is some ambiguity in defining the Fermi temperature when you have multi-band and strongly correlated materials. But nevertheless, there are some trends here. And those trends seem to suggest that there's something interesting going on. Now, it seems like there's a vast desert of white in the lower right, and that's because this plot has been made to highlight unknown things. There's actually a lot of materials populating the lower right, and they're very well understood within BCS theory. But there seems to be absolutely nothing in the upper left. Okay, so is there in fact some kind of a limit on TC, or TC divided by some temperature scale, energy scale, so that no one will ever find a superconductor here? And if there is such a bound, such a putative bound, should be quite strange, because it cannot depend on the mechanism of superconductivity. Because if you look at the systems which lie closest to any conjectured bound, there's magic angle twisted bilayer graphene, two ultra cold atoms, iron selenide and STO with a single monolayer. These systems have very little to do with each other microscopically, other than the fact that they are superconductors or paired superfluids. Okay, so as I already said, that I'm not going to focus on these and many, many other materials not shown here, which are very well understood using BCS theory. Our focus will be to ask, well, can we say something about such a bound? So in the rest of the talk, I would like to show you that we have succeeded in deriving a very general and exact bound in two-dimensional superconductors. It turns out, for the experts in the audience, the bound in general is not in terms of the Fermi temperature or the superfluid stiffness, but I will explain what the bound is in terms of and how it lies on this line. And I also want to say at the very outset, and at the end, I'll explain why the techniques that we use to derive the TC bounds in two dimensions don't quite answer the question in 3D yet. So the question in 3D is open. Okay, so with that,
can I ask a question again?
Yes,
in the
of course.
plot previous. So the materials that show these or the systems that show these very unique close to the Fermi bound, the critical temperature, or as close as that diagonal line that you have, do they actually possess multiple phases where you have a completely insulating phase versus a superconducting phase? And
no, in fact, most superconductors are very far from insulators. It's only the high temperature cuprates, which are all of these triangles, either closed triangles or open triangles, that have nearby insulating phases. So most superconductors are very far from insulators. Okay. So they certainly, so no, they do not necessarily have a nearby insulator. But some of them do, like magic angle twisted bilayer graphene does. The ultra cold atoms do not. And monolayer and iron selenide on STR does not.
Okay. And is it possible to have two phases coexisting in the solid with two different critical temperatures?
No, I don't think it's useful to think in terms of multiple phases in a general section. Yeah. Okay. I think that would not necessarily be a useful.
Okay. Thanks, Paul.
Okay, so let's first ask what determines the superconducting transition temperature. So let me first give you the textbook answer, and then let me tell you why for many of the new systems, the answer might be a bit different, okay? So the textbook question that BCS gave us the answer to is that a metal is like a filled Fermi sea. So in momentum space, all the states inside the Fermi surface are occupied, and that determines EF, or the Fermi temperature TF. And then you can make arbitrarily low energy excitations around the Fermi sea, which give a metal all the metallic properties, okay? And what BCS said was that you might have thought that electrons inside a metal repel each other, but in fact, there are weak attractions. And we don't need to go here into what the cause of that weak attraction here is. If there's any source of weak attraction between the electrons, then in fact, the Fermi surface becomes unstable, and you get an energy gap in the spectrum rather than getting gapless excitations in the metallic state. So if you're from well outside of physics, I think the only thing you should understand about BCS theory is two facts. First, they showed that at the transition temperature TC and below it, the electrons pair up, which is kind of surprising, but true because of the existence of this attraction. And the binding energy of the pairs is called the gap delta. And once you have pairs, even though the electrons were like fermions, which kind of avoided each other, the pairs behave quote unquote like bosons, and you can get a macroscopic condensate. And when you get a macroscopic condensate of pairs, that is superconducting, because single electrons can be scattered by impurities or random vibrations of atoms, but the macroscopic condensate of pairs is too big an object to be scattered by anything, and therefore it just conducts electricity without any resistance. So from this point of view, the transition temperature is just set by the gap. And if the gap is larger, so is the transition temperature. Okay, and this is also taught in all the textbooks that BCS told us how the transition temperature would depend upon the strength of the attraction and so on and so forth. And generalizations of BCS like Migdal-Eliashberg and so on also have this feature that the transition temperature scales like the gap. And this suggests many things. First of all, there is a sensitive, exponentially sensitive dependence on the pairing mechanism. So you might think the stronger the attraction, the larger the TC, or the narrower the band, the larger the BC. So again, from this perspective and its stronger coupling generalizations, there seems to be no real bound on TC. But is this true, or are there limits to the growth on TC? Moreover, as we saw, if such a bound exists, then it shouldn't depend on the details of the interaction at all. So just to repeat, for many, many materials that are really very well understood within BCS theory, there were two aspects, pairing and condensation. The pairing is fragile because the attraction is weak. But once the pairs exist, the condensate is robust. So what kills superconductivity? Whatever is fragile will kill you first. So TC is determined by the binding energy of pairs. But it turns out that in many of the relatively less understood superconductors, just the converse is true. The pairing is very robust, and you might expect that for high temperature superconductivity. Somehow the interactions are stronger. But it's the condensate which is the more fragile of the two phenomena. Okay? And then it's a quantity called the phase stiffness that controls the fluctuations of the condensate that actually determines TC. And there is a background for this both in 2D and in 3 dimensions in the references shown here. So the phase stiffness is going to be very important for us. I'll explain it in much more detail in the coming slides. But it is that which determines how fragile the condensate is. So there's another way of thinking about it. The superconducting order parameter is related to the condensate wave function, which is an amplitude, which is related to the pairing gap, and a phase, okay, the broken U1 in superconductivity. So in BCS theory and mean field theory in general, it's the amplitude which is killed. But in the transitions which are controlled by phase stiffness, the amplitude is perfectly robust, but at TC, the phase is randomized. So since this phase stiffness is very important for us, let's discuss that. So the way the theorist thinks about it is in the left panel. It's the free energy cost for phase fluctuations. So the fluctuations of the phase give rise to an energy which is gradient theta squared, and ds is its coefficient. But for the experimentalist, it has very direct experimental consequences. So as I told you, a superconductor expels weak fields. So if the field outside is B, inside the superconductor, the magnetic field decays with a characteristic length scale, which is called the penetration depth, lambda sub London L. Okay, so this London penetration depth is directly related to the phase stiffness up to universal constants E, H bar, and the permittivity of free space. Sorry, this is the mu naught, whatever it's called in SI units. Another way in which you can think about the optical conductivity is that you have a superconductor. So if you look at the frequency dependent absorption in a superconductor, real part of sigma omega versus omega, then you have an infinite DC conductivity. And in fact, that infinity is a delta function at the origin. And then, of course, you have a gap, so you have no absorption at low energies. And then at higher frequencies, you will get some complicated absorption pattern. The strength of this delta function is also related precisely to the stiffness ds with universal prefactors. Okay. Now, for some people in the audience, the idea of a superfluid density, n sub s, may be more familiar. That's because when you have a simple parabolic dispersion, when the energy momentum relationship is just k squared over 2m, then the superfluid stiffness can be written as the superfluid density divided by the effective mass. So both the numerator and the denominator have a physical meaning. But if you have a non-parabolic dispersion, or if you have multi-band system, which many systems are, then the numerator and denominator do not have independent meaning, but the combination does, and that is what the superfluid stiffness is. Okay, so now let's talk about the two-dimensional theory of superconductivity, which is the theory of Berezinski, Koslitz, Thouless, and you'll immediately see why there the superfluid stiffness plays a major role. Because in two dimensions, as these authors pointed out in very famous work, what drives the superconducting transition is the disordering of the phase due to the unbinding of vortex and anti-vortex pairs. Okay, and then you can see that the TC in two dimensions is determined by the balance between energy and entropy of vortices, and this phase disordering is determined by ds. So to make that precise, in two dimensions, the superfluid density has a jump discontinuity at Tc, and the value of this discontinuity is related to Tc via a universal amplitude ratio. So Tc is just tied to the stiffness just below Tc by universal numbers that are obtained from a renormalization group calculation pi over 2. And we will use this universal relation to great effect as we proceed. Okay, so now let me talk about the work that we have done on upper bounds. And I apologize to the audience of non-physicists that I will have a fair number of equations on the coming slides. You can completely ignore all the equations and just look at some of the words or listen to me, and you'll be fine. The reason I have these equations is the following, that when a theoretical physicist uses the word upper bound, he's not saying something vague. He's trying to say something very precise so that there are less than equal to signs. And therefore, I just want to be sure that I communicate to you, or at least the experts in the audience, that something rather precise has been done. So with that caveat, let's proceed. So to prove any theorem, physicist theorem of this sort, you have to have a starting point. So I'm going to start with some low energy effective Hamiltonian, which contains the kinetic energy of all the electrons in the active bands that are involved in superconductivity. So epsilon sub m is the band structure, k is the crystal momentum, m is the band index, sigma is the spin. So this is describing the electronic structure of the system. And then I'm going to say, I am going to be agnostic about the mechanism. Let it be any interaction energy that gives rise to pairing and superconductivity. Now, of course, to prove something, you have to have some assumptions. So here is the key assumption. To compute the stiffness, I will need to ask, how does the Hamiltonian couple to an external vector potential? And I'm going to say that the vector potential only couples to the kinetic energy and not to the interaction. So if you had a continuum description, that's just obvious because you just have minimal subtraction, p goes to p minus Ea. On a lattice, what that's going to entail is that every time an electron hops from a site j to k with a hopping amplitude t, t of j sub k acquires a Pile's phase. So it recognizes that there is a vector potential. Now, how general is this assumption? So this is valid for a very broad class of interactions: electron-phonon interactions, electron-electron interactions, ultra-cold Fermi gases. But is it always true? And the answer is, of course not. You can write down Hamiltonians for which this would make no sense. And at the very end of the talk, I will turn to the case where you have completely flat bands, a topic of great interest currently, where there is no kinetic energy. So of course, if you have no kinetic energy, then you can't couple the vector potential to that. So for now, let's ignore such things and let's look at the vast majority of systems where this is a perfectly natural assumption. And let's see what we can do. So here we compute the superfluid stiffness using linear response theory, and using the positivity of spectral functions and nothing other than that, we can find an upper bound on the superfluid stiffness in terms of a quantity d tilde, which has a very simple physical meaning and is also much simpler to estimate. So I will explain what that physical meaning is. For my theory friends here, I've written down the transverse current correlation functions, and I show the Lehmann representation from which we can show that the terms I'm neglecting are positive definite. So this is a perfectly good upper bound. So what is d tilde, which is upper bounding the stiffness? So for that, you can again ignore all the equations, just go back to the optical conductivity, which is a delta function whose weight is ds. Now, it turns out that there is a very general sum rule which says that the total area under this curve, including the delta function, which is called the optical spectral weight, is d tilde. So it is no surprise that the total area under this curve is more than the area under part of it, which is the delta function. And that is the content of the bound that I showed you on the previous slide. Okay, now this slide is really for experts, but we were able to derive a very general expression for this upper bound d tilde in terms of something which looks horrible, but is rather straightforward. So you remember in parabolic dispersion, it was density divided by mass. The density gets replaced by a density matrix. The mass gets replaced by a inverse mass tensor. But the nice thing about this equation is that everything that I show in blue depends only on the band structure, and then everything that I've circled in red depends on interactions and temperature. And then by disentangling this, we are able to make a lot of progress. Okay, so now let's ask, how does our bound work out? So I told you that in 2 dimensions, we are standing on the shoulder of giants, Berezinski, Koslitz, and Paulus. So TC is related to the stiffness at TC. And in any dimensions, we have derived a general bound on ds using our upper bound d tilde. So now we have an exact upper bound, which does not use mean field theory, and which is completely independent of pairing mechanism or strength, modulo the assumptions that I already stated. Now, it's not immediately obvious whether this bound is useful, because there seems to be TC on both sides of this bound. So in the rest of the talk, I want to show you that this bound shines when you have low density, narrow bands, and strong correlations, precisely the regime where BCS Eliashberg fails. And conversely, even though this bound is always valid, it will be ridiculously high and not particularly useful when BCS mean field theory works. So at least we have something which is completely complementary to the conventional approach to thinking about TC. Okay, now that's the very formal result, and that's useful only to the extent that it gives you something useful for the real world. So we've applied it to a series of ever increasingly complicated examples, and maybe I'll go through some of them, okay? Starting with the spherical cow of parabolic bands and ending with twisted bilayer graphene. So let's do that. But before I do that, are there any questions? Let me just take a break and see if there are any questions.
Sorry, may I ask a question, please? Is it possible?
Yes.
Yes, please.
Okay, Mohit, sorry, and please feel free to ignore it if it's, I don't know, not appropriate. But just if you could take just 2 minutes, as a particle physicist, I mean, when you defined the superfluid stiffness through the Meissner effect, it seemed very much like the mass of the gauge boson, which was getting massive. Is that
Yes,
roughly correct?
it is roughly correct. Yes.
Okay, and then you went through it very fast for me, but when you wrote down the layman representation, it seemed roughly to me that you were doing the following. The gauge potential A would couple to the current J, and if I'm looking for a mass term, which is like m square, A square, I would take two derivatives with respect to A, so I'd get two currents, and then you insert a complete set and you use some kind
Yes.
of positivity. Was that roughly
Yes.
correct?
That is 100% correct. That is exactly what we do.
Okay.
And the reason why you get two terms in the first line below the blue line is because actually the current has a paramagnetic piece because it's P minus EA. So there is a term which is already proportional to A, and that gives you the diamagnetic piece D tilde. And the current correlation gives you the paramagnetic piece. And actually, I'm just appealing to the positivity of that to say that the diamagnetic piece is an upper bound on the superfluid stiffness.
I see.
So that is actually 100% what I do technically.
Okay.
But intuitively, this is the easy way to understand it.
I see. And can you just repeat this slide once more? Sorry, just once.
This slide is that just let's not worry about any equation. Here is the optical conductivity, the real part of the conductivity, sigma of omega, plotted versus omega, which is the frequency. That's why it's called optical conductivity, frequency dependent conductivity. Because I have a superconductor, I know I have an infinite DC conductivity, but actually that infinity is a delta function with finite weight. And that weight is precisely related to ds, okay? And the total area under everything, delta function plus all finite frequency absorption, is related to this upper bound d tilde. So the weight in the delta function is upper bounded by the total weight under this curve. That's a nice, easy way to think about it.
Okay.
But technically, we did what we just discussed in the previous slide.
Okay. Thank you very much.
Mohit, one question.
Yes.
Is, optical sum rule, I mean, of course, in general, you should probably go up to infinity, but for practical purposes, you would like to stop at some desert area, like where some higher band. Is it clear, like, in every where that separation should be?
So that comes to the question of what is the best low energy description of your superconductor. So if you start with a given low energy description, that tells you how far in frequency you should integrate.
Right. I was thinking operationally, just from experiment.
So operationally, we can go through this. If you have isolated bands and you think that certain bands are going to remain forever empty, others going to remain forever filled, then you just stick to that. In parabolic dispersion, there is no cutoff whatsoever, okay? That's fine too. So it depends on what system you look at. But it's a very good question, but it relates to, you must start with some description and then you can bound using that description. Okay, so let's start with a parabolic band. So this story is quite simple because now you have a dispersion which is parabolic, you have a density of particles, and you have a Fermi energy, which just relates N and M to this energy scale. And now you can put any interaction that leads to superconductivity and pairing. I don't care, okay? Now, the first bound, the ds is bounded about by d tilde, is a very simple bound which nobody can argue with, that the superfluid density is less than or equal to the total density. And the second bound tells you that no matter what you do, Tc has to be lower than 1/8 the Fermi temperature. Now, this result is actually rather simple and could and should have been derived decades earlier, but wasn't, okay? Possibly because people were never thinking about TCs, which were as high as a fraction of the Fermi energy. But you could just take this equation and draw it as a line on this Mura plot, and you would look very happy. But you have to be a bit careful because actually this is derived only for parabolic dispersion. And many of the materials, most of them in fact, are not simple parabolic dispersion. However, like many things, the spherical cow result is a very good idea to give you a general feel, like Drude theory. So in that sense, it tells you that there is some meaning to plotting TC over EF. And of course, later on in the talk, I will tell you exactly what happens when you get to non-parabolic dispersion and how seriously you should take the parabolic result. But for now, let's explore this because there, in fact, you can test this quantitatively for systems which do have parabolic dispersion. So let's first discuss the BCS-BEC crossover in cold atoms, where I would have thought the first experiments would have tested this result. But that has not happened so far. But very soon after our paper, there was this beautiful work by the Iwasa Group in quantum materials, which actually tested this bound. So I want to tell you about both. So quickly, the BCS-BEC crossover. Okay, so I already discussed the BCS pairing regime, where you have very weak attractions. So the Cooper pairs whose size is C naught, the spatial extent of the pair, is much, much larger than the interparticle spacing. So in real space, you get this horribly overlapping set of pairs, but BCS solved this limit for us. You could imagine going to the opposite extreme where the interaction between the fermions is the strongest energy scale in the problem, in which case you get tightly bound bosons like molecules. And these bosons condense, okay? And you could imagine, at least in theory land, that you just smoothly change the attraction all the way from a very weak attraction all the way to BEC and look at the BCS-BEC crossover. But this is not just theory land. In ultra-cold atomic gases, this has been realized in the lab because you have the means of increasing the attraction at will. And in fact, it is the very strongly interacting regime right in the middle of these two limits, where the pair size is of the same order as the interparticle spacing, which is in fact the most interesting regime in the BCS-BEC crossover. Now, if you look at everything that's known about the 2D system, then I plot those results in this graph where I have T divided by TF on the vertical axis and pair size divided by interparticle spacing on the horizontal axis. So small pair size is the BCS limit in the right. Sorry, I meant just the opposite. It's actually the inverse pair size that I'm plotting here. Excuse me for that. So near the origin, I have BCS theory with huge pairs. And on the right-hand extreme, I have very tiny pairs. So I have the BEC regime. I have drawn known results from BCS theory as the black asymptote here, known results from the BEC regime as the dotted asymptote here, because in 2 dimensions in the extreme BEC regime, TC must go to 0. 2-dimensional bosons have no condensation, but interacting bosons do. And I've drawn my bound as the red line here. And the blue line is pure conjecture. There's no calculation, okay? But it does seem like in the strongly attractive regime, interacting regime between BCS and BEC, this bound should come close to being saturated. And this is a result that is out there and should be tested both by experiments and quantum Monte Carlo simulations. What came as a huge surprise was this experiment by the Iwasa Group in Tokyo. So they took this seemingly very complicated material, which is a layered system with a parabolic dispersion, a density of states, which shows that it really is a 2-dimensional material with a jump discontinuity and a constant density of states. Now, of course, in the solid state, unlike in cold atoms, you have no means of tuning the attractive interaction. You have what you have given by nature. But the genius of Yoshi Iwasa's work is, and he has been doing this for decades now, is that using ionic gating, he's able to tune the density of carriers, which is very hard to do in the solid state in general. And using lithium intercalation and ionic gating, they were able to tune through the BCS-BEC crossover. And on the Mura plot, I show Iwasa's data in the blue diamonds. And when they went into the crossover region, they basically saturated our 2D bound and just came there. They have not gone beyond it. They have not been able to tune beyond it, but they have found that they have saturated it and reached TC of 1/8 epsilon Fermi in this very low density material that they are looking at. Okay, how much time do I have? Rajdeep, Jyotishman?
Yeah, so we are at 5. I guess we started a little late, around 4:15, I guess. So maybe
Okay,
10
so
minutes.
15 minutes. So
10
let me
minutes.
skip the details on this model, but I just want to say that if you compare it with certain model situations where you first look at non-parabolic bands, you again found that the bound can be extremely useful, so that in weak coupling in this non-parabolic band model, this is BCS theory, it would say that the TC goes to zero in weak coupling and then just goes on increasing without bound. Whereas if you do sign problem-free quantum Monte Carlo, you can show that TC actually goes up and comes down, and our bound is able to capture this strongly interacting regimes rather well, whereas BCS theory greatly overestimates TC. So even though the pairing is very strong, the fluctuations of the phase are determining TC. So this is sort of telling you when is the bound useful and when it is not, when you compare with the best known numerical results. Uh, Let me discuss magic angle twisted bilayer graphene. So as I already told you, the MIT group showed in 2018 that when you take two sheets of graphene and twist them at just the right angle, you get extremely narrow bands. And that's why even in a material made out of carbon, you get very strong correlations, and you get correlation-induced insulators at filling factors where band theory would have told you that you should have metals. And near these correlation-induced insulators, you get superconductivity. So here the band structure is much more complex, but the experiments do show that you have a BKT transition. The pairing mechanism is totally unknown. Maybe it's phonons, maybe it's electron-electron interactions, but that's where our bound is good. All we really need is the band structure. And it turns out that you have to have 8 bands, including valleys, spins, and layers. And the bands have some topological character, which unfortunately I have no time to get into, which is very important because that may act as a obstruction to getting exponentially localized Vanya functions. But let me leave that for the experts. So what we did is we took one of the standard band structures derived by Koshino and Fu based on the Bistrisker-McDonald model, or we could take the Kang-Wafek band structure, and we can evaluate this inverse mass matrix for that band structure. So that would give us this inverse mass matrix. But what do we do about this pesky density matrix, C dagger C? So we could play just a mathematical physicist and say that we define an inner product in the space of operators through some thermal expectation value, use standard inequalities like Cauchy-Schwarz to say that therefore this is upper bounded by the momentum distribution, say that the momentum distribution is bounded by 1 in any Fermi system. And using such very standard mathematical physics tricks, you can get a rigorous bound that independent of any information about the interactions, if this is the band structure, the transition temperature in the system can never be more than 48 Kelvin. So this is an order of magnitude larger than what is seen in nature. But once you have expressions like we have in the upper box, you don't necessarily have to play mathematical physicist. You can also just estimate the upper bound. And if you make the simplest approximation, saying we took M inverse from band theory, so let's just take the thermal expectation value of C dagger C also from band theory, the Fermi function, you get an approximate answer. This is not a real bound, which is why I have a tilde here, which is 6 Kelvin. So you can see that these kinds of expressions can give you useful answers in many situations. And I'm not showing you what we get for iron selenide on STO and many other situations. Okay, so let me spend just 2 minutes on this problem of flat bands. So flat bands are very interesting because flat bands are bands which have zero dispersion. So there is no kinetic energy. So in fact, you might ask, if there's no kinetic energy, then how can electrons move? And if electrons cannot move, how can you even get conductivity, let alone superconductivity? So there's very important progress made on this using mean field theory. by the group of by Torma and collaborators. And it involves the quantum geometry of the wave functions, like concepts like the quantum metric of these wave functions. So the question we asked ourselves was that can we obtain any exact results without resorting to mean field theory? And the reason is that if you have a band structure in which you have a completely dispersionless band or a very, very non-dispersive band, which is isolated from other bands, then there's no small parameter. Any interaction you put on the zero bandwidth system is infinitely larger than the bandwidth, okay? Secondly, you cannot couple the vector potential to this kinetic energy because there is no kinetic energy. We could use the multi-band bound that I just discussed above, but it's not optimal because it includes interband spectral weight, which was the question that Raddeep was asking. You certainly have spectral weight for causing optical transitions from this flat band to the other bands, but we don't want that. We want to just ask what is happening in the flat band. And finally, if the bands are topological, in addition to being flat, there's an obstruction to exponentially localized Vanya functions. So how do you even get a tight binding description to start the calculation? So I'm really just posing the questions, and I'm just saying that all of these questions have been addressed. And in fact, very interesting low energy spectral weight bounds in terms of the quantum geometry of these wave functions have been derived in our recent papers, which appeared in PNAS, at least for a certain class of models with flat bands. But I think I will not go into that because we are running out of time. So I was planning to tell you about quantum geometry, and then I was planning to show you bounds like this, that the low energy spectral weight in these flat bands are bounded above by a quantity which looks like this. So you can understand why you get n times 2 minus n, because if this band is completely empty, n is equal to 0, or completely filled, n equals 2, then of course it is insulating. So there is no low energy spectral weight at all. You need interactions because without interactions, there would be no transport. So it's proportional to the interaction energy. And then this omega is the spread of the Vanya functions. And that's where the quantum geometry enters here. And there is a upper bound in terms of the Marzari-Vanderbilt spread and a lower bound in terms of the quantum metric. And we can compare it with mean field theory and also in some cases the quantum Monte Carlo. The one thing that I do want to emphasize here is that the upper bound on TC we get here is most definitely not a bound on TC over epsilon Fermi. Because if you park your chemical potential in this flat band, then it's perfectly sensible to say that epsilon Fermi is 0, in which case TC over epsilon Fermi is infinity. But that's not the right thing. Here, what you should look at is the bound in terms of the low energy spectral weight, as I've been emphasizing. So we've also generalized this to topological flat bands, and I'll discuss this with the experts on some other occasion. For the experimentalists, I want to point out this recent paper that I've been involved with, written by my experimental colleagues, Jeannie Lau and Mark Boproth, where they have actually measured in a very interesting way the superfluid stiffness in magic angle twisted bilayer graphene, which is very hard to measure using conventional methods, using a clever combination of the critical current and the coherence length. The idea of using this clever combination comes from a paper that Rajdeep actually wrote as part of his PhD thesis many years ago. Okay, so let me conclude in the last 5 minutes by at least just telling you why the upper bound on TC in 3 dimensions is an open question. So there are 3 challenges. Okay, the problem of bounding TC in 2 dimensions is, I think, largely under control, but the challenges in 3D are threefold. First, there is a misconception in the community that the BEC transition temperature in 3 dimensions is an upper bound because you can plot it here and it looks like an upper bound, but actually it is not, okay? The second thing is that when you look at, so actually the fact that it does not cause a lot of confusion over many years with everyone from Feynman and Lee and Yang and so on contributing to the confusion until some mathematical physicists proved this rigorously, that the BEC temperature is not an upper bound, okay? So We do know, for instance, in the BCS-BEC crossover, that TC over epsilon Fermi is maximum value is 0.22, but this is only known from experiments in quantum Monte Carlo. We don't have an analytical handle on this upper bound. And one reason why we don't have an analytical handle on this upper bound is that unlike in 2 dimensions, ds does not have the dimensions of temperature or energy. And that you can just see from dimensional analysis. You don't have two powers of space in the measure, you have 3 powers. And so actually the relationship between TC and ds has an ultraviolet cutoff. The coefficient becomes non-universal. And then the question of bounding this non-universal prefactor is not open. So you don't have the analog of this universal BKT result. And finally, no time to go into it, there are also issues near quantum critical points that create problems in 3 dimensions. Anyway, so I think it's coming up on 5:15 for you guys. So let me end by putting up my summary slide, and I am very happy to take questions. Thank you very much.
Thank you, Mohit. That was fantastic. And you were perfectly on time, even though we lost like 5 to 7 minutes because of preparation of the other stuff. So, so questions from the audience. I'll invite, there are a few chat questions. There is one chat question from Unmesh. So Unmesh, I think you can unmute yourself and ask this question directly. Unmesh, is it possible? Unmesh?
Okay, I can read his question if you want.
Yeah, I can read too. Yeah, that's not a problem. So one initial assumption to get the upper limit of the TC was that vector potential couples with the kinetic energy. But for the TBLG, the kinetic energy is very, very small. Is there any modifications in the model to take care of the fact in order to get the 6 Kelvin limit?
No, the answer is you do. I mean, the twisted bilayer graphene is not 0 bandwidth. It does have some kinetic energy. And so if you can write down a theory which is just based on the 8 bands which are in the low energy sector without involving higher bands, then you can just proceed as I did. So there is no problem. If in fact you want to go to a model system where the kinetic energy is 0, well, then you have to go to the second half of my talk, which I really rushed through. But you can look at this PNAS paper, which is at the bottom of your screen on the right-hand side, where we talk about what happens when you have a completely flat band.
Okay, thank you. The next question is from Pratap Chandra. Let alone superconductivity, flat band means 0 kinetic energy, hence normal conductivity is not expected. Still, we get conductivity in twisted graphene systems. Could you please elaborate?
So again, I want to say that graphene, twisted bilayer graphene is not 0 kinetic energy system. The bandwidths are known to be of order 10 millivolts there, experimental. But if you have a model with 0 kinetic energy, then interactions can lead to transport and conductivity there. And again, I refer the person who's asking the question to look at this PNAS and references therein.
Okay. Okay. Thank you. Questions from the audience directly? Are there any questions?
Hi. I had a question. This is Mandar.
Yeah.
Thanks for a
Hi, Mandar.
Thanks for a very nice talk, Mohit. I had some more technical questions about the, analysis in Mark Bokrath's paper. I was wondering if you would be willing to
yes,
maybe answer that in a separate talk.
Yes, let's do that separately, because I didn't talk about that at all. And yeah, that's much too technical for a colloquium, but I'd be happy to do that, Mandar. And we could even get Mark and Jeannie to join if you wish.
Okay, thanks.
Sure.
Okay.
Mohit, one question in this final version of where we're talking about the quantum geometry, like the completely flat band, is that answer model dependent? Like I'm guessing you took a Hubbard model or something like that. It gave you the scalar view. So
yes. So the thing is, yes, we do not know. So the things that I talked about in the first half of the talk, and which are summarized in the left-hand panel, are done in a very model-independent way. Okay, we do not yet know. By we, I just don't mean me, but the entire community. How to do that in such a model-independent way in a flat band system, partly because you see any interactions will have a very dramatic effect on the physics in a flat band. And so different interactions may lead to very different states. So if you put repulsive interactions in a completely flat band system, you would generally expect to get magnetism. And there are some rigorous results due to Elliott-Lieb on that. You get ferromagnetism. So we just put in by hand attractive interactions, which again, using Lieb's idea, give you superconductivity, at least in the ground state. So certain things are known about the off-diagonal long-range order at zero temperature in the Lieb lattice in the presence of attractive interactions. And it is precisely for those systems that we found bounds on the superfluid stiffness, for instance.
I was wondering, suppose we had just a whatever nearest neighbor version of.
Yeah, so I think one would have to work that out because the problem becomes quite complicated at that point.
And the other thing is your answers, even in the first part and here, is agnostic about the symmetry of the order parameter, right?
Modulo the assumption that you have a BKT transition, because you could imagine an order parameter which is rather more complex, and the topological defects don't even look like vortices. If that's the case, in most cases, you would expect that in 2 dimensions, TC would be 0, actually.
Right.
Okay, using Mermin-Wagner theorem.
Yeah.
So to the extent that you have a finite transition temperature in 2D, that means whatever your order parameter, it's just breaking U1 at 0 temperature. Okay.
Yeah.
And so then it doesn't matter beyond that.
Okay. Okay. I answered very good.
Okay.
Any other question?
Sorry, can I ask? Can I ask?
Yes, Sandeep, please.
Jyotishman?
Yes, please.
Okay, thanks a lot, Mohit, for a very interesting talk. I'm sorry I understood it poorly, but let me ask this. I'm really having a hard time understanding this basic result in 2D, I guess, due to your giants. That KBT is related to DS. And just to put it from a particle physics perspective, so you can correct me, the transition temperature should be related to the pairing energy, right? Isn't that correct?
No.
No? I see.
And the answer is that the pairing energy is much higher.
Yeah, okay.
You see, the thing is, so this goes back to, okay, at least at an intuitive level, it goes back to what I had on this transparency. Whatever can kill you will kill you. So are the pairs fragile? In which case the transition temperature will be governed by the delta.
Okay.
But if the phase coherence is the more fragile of the two, then it's governed by DS. Now it turns out that if you work in the BCS limit, where you have very large pairs compared to the interparticle spacing, then it turns out that the BCS temperature and the Kosterlitz-Thouless temperature are very, very close to each other. Okay, they differ only by order TC over epsilon Fermi. But even by that exponentially small number, the BCS mean field temperature is higher than the Kosterlitz-Thouless temperature. Okay, but if you go to stronger couplings, the BCS mean field temperature at which no phase transition happens is much larger than the Kosterlitz-Thouless temperature.
I see. Okay, I got it. Okay, so it's where you kill your your gauge boson gets a zero mass, and not where the Higgs gets a zero mass, so to say, in particle physics language.
Well, I mean, it is when the system shows superconductivity. That's the easy way to think about it. When do you get zero resistance?
Right. Now, I was just trying to understand.
There is only one phase transition. So I think by saying when something gets a mass or something else gets a mass, one loses track of the fact that there is actually only one phase transition, where there is a singularity in the thermodynamics, a singularity in the response functions. And so we are looking at that TC at which something singular happens.
I see. And then why, what is the physics in that relation that KBT is of order ds at the transition?
Okay, so actually, if you look at the original Kostels-Thouless paper, it just comes from an energy entropy balance.
Oh, you mean just that old, not the argument about the vortices?
Yeah, it's about the if you have an isolated vortex,
Yes.
okay, then basically its energy is log divergent
Yes.
because of the kinetic energy of the superflow around.
Correct.
But then you can put it anywhere in the 2D plane, and that gives you a logarithmic gain in entropy. And when you just balance the energy versus entropy, you get TC is of order ds. Now, this argument, is perfectly correct, but it would seem to relate the TC to the superfluid stiffness at zero temperature. But of course, what you should do in a more correct calculation is to relate TC to the superfluid stiffness at TC, because it's that which is going to be important. So and that's what this renormalization group calculation of Nelson and Kostels does. And even the pi/2 comes out correctly in Kostels and Thouless. The big change is that instead of getting ds at 0, they find ds at TC minus. So they get the jump discontinuity. That's the subtlety. But that subtlety is not particularly important for anything I did. But I'm using...
Sorry. Go ahead.
Okay, and you might have thought from Kostels and Thouless's original argument for pi/2 that pi/2 is a number that came out from the simple estimate. But what you get from Nelson and Kostels is that actually, nope, it's a universal amplitude ratio, which is independent of all microscopic details.
I see.
Okay. Thanks, Sandeep. There's one last question. Vaibhav, you can unmute and ask this question.
His microphone is not working, Jyotishman. You might want to read it.
Okay, fine. So for the 2D structure, one can get the upper bound by this way, and hence say one can design the band structure to push the upper bound. However, what is it that can stop any such material to reach its upper limit?
So I wish I knew the answer to that, because then I would patent it immediately, right? So of course, the question is a very valid one, right? Because this is just telling you what the upper limit is, not whether you can reach it or not. So what you would like to do is to look at systems where the pairing interaction is the strongest possible. Because if the pairing interaction is very weak, this may be the upper limit, but actually the pairs just won't form there, right? So the actual TC is, in some sense, the minimum of this upper bound and any mean field bound that you would get from BCS like mean field theory. So you need to tailor both the band structure and the interactions to reach it. The point of the work that we did was to show that there are many novel materials that seem to be reaching close to this upper bound. And this upper bound is substantially independent of whether they are cold atoms or lithium-doped zirconium nitrochloride or twisted bilayer graphene. But I have no magic wand to say, here, make this material and it will superconduct at a very high temperature. I wish I did.
Okay. Thank you, Mohit. Okay, so I think with that, we come to the end of this session of the Wednesday Colloquium. Mohit, thank you for doing this early in the morning and being patient with our technical snags. We thoroughly apologize for the initial 7-minute delay. But it was a very enjoyable lecture, even for non-specialists like me. And thank you for providing a bird's eye view of this idea of the upper bound for TC. Next week, we are actually having Professor Michael Kramer from Max Planck Institute of Radio Astronomy. He is going to talk about some of the most amazing results that have come out recently, probing relativistic gravity with radio astronomy. So please be there at 4 p.m. sharp next week to join again in this NSF Wednesday Colloquium series. And I would like to also thank everybody in the lecture room, and especially who still stuck back and listened to the talk, sitting there, even with the network problems. And also the staff, the lecture room staff, for doing a fantastic job of recovering back from this problem. So, and with that, I would like to thank the Zoom audience as well, and those who can make it. And this is for Mohit. Those who can make it, please join for tea and snacks. so thank you, Mohit. We'll look forward to hosting you physically here sometime.
Yes.
And have
Very
your
much. I'd also look forward to visit.
Sure. Okay.
Thank you.
Thank you very much.
Okay. Bye.
Bye.
Bye. See you.
Bye.
Bye.
Thank you, Rajdeep.